James Webb once again challenges scientists to rethink our understanding of the universe. In its latest discovery, the telescope has detected a key building block of life at the dawn of the universe, overturning what we know about the first galaxies. The discovery of a cloud of carbon in a distant and compact galaxy, appearing just 350 million years after the Big Bang, marks the earliest detection of an element other than hydrogen in the universe. These groundbreaking results have been accepted for publication in the journal Astronomy and Astrophysics, with a preprint version available on Arxiv. Co-author Roberto Molino, a professor of experimental astrophysics at the Cavendish Institute for Cosmology at the University of Cambridge, stated, "Earlier research suggested that carbon began forming in large quantities about 1 billion years after the Big Bang. However, our discovery indicates that carbon formed much earlier, possibly making it one of the oldest metals astronomers classify. Astronomers classify elements heavier than hydrogen and helium as metals because they were forged inside stars' fiery furnaces and spread throughout the universe by supernovas. This process was once believed to take many star lifetimes before enough heavy elements were available to form planets. However, the new discovery by James Webb challenges this notion. In the remote galaxy GSZ-12, which is 100,000 times less massive than the Milky Way, James Webb detected traces of oxygen, neon, and a significant signal of carbon. The mechanism behind carbon's early formation remains unclear, but researchers speculated may involve stars collapsing with less energy than previously thought, allowing carbon to escape and seed the early universe. This discovery raises intriguing questions about the timeline of life in the universe. It suggests that life might have emerged earlier than previously assumed, under conditions possibly quite different from those we know. Perhaps there are forms of life not based on familiar ingredients like proteins, but on entirely different structures, such as crystalline or metallic compositions. This speculation leads to the famous Fermi paradox. If life could emerge earlier and in unexpected forms, why haven't we encountered other intelligent civilizations? To understand the potential for intelligent life in the universe, we must consider the steps that led to our own existence and explore diverse scenarios where life could arise. It's crucial not to rely on unfounded assumptions or logical fallacies, such as conflating absence of evidence with evidence of absence. The Fermi paradox challenges us to estimate what's out there quantitatively and accurately, avoiding simplistic point estimates and acknowledging uncertainties. The Drake equation, a tool used to estimate the number of active, communicative extraterrestrial civilizations in our galaxy, provides valuable insights into these questions. By breaking down the problem into manageable components, it invites us to consider the vast possibilities and uncertainties inherent in the search for intelligent life beyond Earth. In summary, James Webb's discovery of early carbon formation in the universe not only reshapes our understanding of cosmic evolution, but also prompts deeper reflections on the nature of life and intelligence in the cosmos. It invites us to contemplate a universe where the emergence of life might be more diverse and ancient than we have imagined. Calculating the potential for intelligent life. For example, we could measure or estimate factors such as the rate of star formation in the Milky Way, the proportion of stars with planets, the average number of potentially habitable planets around these stars, and so on. By multiplying these factors together, we could estimate the number of active civilizations we might detect today. However, this approach encounters significant challenges. Firstly, while we have a good understanding of the rate of star formation in the Milky Way, if we simply multiply this rate by the age of the universe since the Big Bang, we'd expect far fewer stars than actually exist. Estimates suggest the Milky Way should have formed around 10 billion stars throughout its cosmic history, a seemingly large number. Yet, this is only about 2 to 3% of the estimated 400 billion stars in our galaxy. The flaw in this calculation lies in assuming a constant star formation rate over cosmic history. In reality, star formation has varied significantly. It began roughly 200 million years after the Big Bang, peaked after about 3 billion years, and has since been declining. Local events like interactions with satellite galaxies and gravitational influences from nearby galaxies like the Magellanic Clouds and Andromeda have also influenced star formation rates. Moreover, the Drake equation, initially a monumental achievement, assumed a static and eternal universe, a concept refuted by our understanding of cosmic evolution. The universe began with a hot, dense Big Bang and has been evolving ever since. Today, we have a more nuanced understanding of our universe within and beyond the Milky Way. We know the types of stars that exist, how heavy elements and rocky planets form, and the conditions necessary for complex chemistry and potential life. Our knowledge of exoplanets has similarly expanded. From detecting our first exoplanets just 3 decades ago, we've now confirmed nearly 5,000. While there are detection biases favoring easier-to-find planets, we've developed methods to correct for these biases. This data allows us to estimate the prevalence of planets around stars, their composition, and their potential to support life. In our modern understanding of the Milky Way, we can reasonably estimate the number of potentially habitable planets. This progress represents a significant shift from the speculative beginnings of the Drake equation, where uncertainties about star and planet formation dominated, estimating potentially inhabitable planets and life's origins. In fact, we can perform this calculation in various ways to illustrate the depth of our understanding. Of the approximately 400 billion stars in the Milky Way, about 80% are red dwarfs, 18% are similar to the Sun, and only 2% are too massive and short-lived to support life. Each stellar system likely hosts between 5 to 10 planets, with 1 to 2 planets in the habitable zone around each Sun-like star. Approximately 20% of Earth-like planets orbit Sun-like stars, a higher proportion among red dwarfs. Using these conservative estimates, we can calculate the potential number of inhabited planets in the Milky Way. Number of stars, 400 billion. Proportion of Sun-like stars, 18. Expected habitable zone planets per relevant star, 1.5. Fraction of habitable zone planets that are Earth-like in size, 20. Multiplying these figures gives us an estimate of approximately 21.6 billion potentially habitable planets in the Milky Way. It's sensible to round this to 20 billion, considering uncertainties in these numbers. However, several uncertainties persist: variations in star formation rates, the metallicity of stars affecting planet formation, and the actual existence of planets around stars. They could feasibly be as few as 5 billion or as many as 50 billion potentially habitable planets, accounting for uncertainties in our data. Factors like planetary moons, the presence of gas giants, distance from the galactic center, and stellar system configuration may not significantly impact habitability estimates. Beyond these uncertainties lies profound cosmic ignorance. While we know life's building blocks are ubiquitous across the universe in asteroids, galactic centers, and exoplanet atmospheres, we understand little about life's origins. Carl Sagan once estimated a conservative 11% chance of life arising from non-life, but such figures remain speculative. Questions abound. How frequently does life arise and persist over billions of years? How often does it evolve complexity, multicellularity, or technological civilization? The rarity of such events may liken them to winning the lottery multiple times in a row. Considering Earth's journey from simple life to advanced civilization took over 500 million years, driven partly by chance, raises further questions about the likelihood of similar developments elsewhere. These uncertainties underscore our limited understanding of life's complexities and its potential prevalence in the cosmos. Life, civilization, and the search for exoplanets. Furthermore, how long does technologically sophisticated life endure? Does it ever become a multi-planet or interstellar civilization? Or does it progress from advanced to extinct relatively quickly? At this point, our uncertainties are so significant that it's plausible humans might be the sole intelligent life in the Milky Way or even the entire observable universe, which likely contains over 1 trillion times more stars than our galaxy. Roughly estimating, there could be around 20 billion Earth-sized planets, composed of similar elements to our own, orbiting at the right distance from their stars to support liquid water assuming Earth-like atmospheres. However, the crucial question remains, how many of these planets actually harbor life? It could be most, many, or only a tiny fraction of those that are suitable. Before considering longevity, colonization, or machine-based life, we must acknowledge the possibility that the Fermi paradox is resolved simply because intelligent, technologically advanced, space-faring civilizations do not exist. Without evidence to the contrary, this hypothesis should remain our default stance. In addition to reshaping our understanding of life in the universe, James Webb is revolutionizing exoplanet science. Detecting exoplanets was once so challenging that scientists first identified black holes, detected the cosmic microwave background radiation, and observed countless distant galaxies before discovering the first exoplanet in 1992. Today, astronomers have identified over 5,000 exoplanets and continue to discover more. Despite these advancements, our knowledge of these distant worlds remains limited. Artists' renditions often depict speculative landscapes based on mass, radius, and distance from their stars. However, the James Webb Space Telescope is transforming our view of exoplanets by studying their atmospheres in unprecedented detail. By analyzing starlight filtered through exoplanet atmospheres, Webb can detect chemicals like water, carbon dioxide, methane, and more, providing insights into their compositions and formation. Webb's planned 10-year mission promises to answer fundamental questions about exoplanets, including their chemical makeup, formation processes, and whether our solar system is unique or typical in our galactic neighborhood. Here are 5 major planetary puzzles scientists hope to solve with Webb. Atmospheric mysteries. Why do some rocky planets have atmospheres while others don't? Webb aims to identify a cosmic shoreline, a theoretical boundary that separates worlds with and without atmospheres based on factors like solar radiation and gravity. Exoplanet habitability. What conditions make a planet potentially habitable? By studying atmospheric compositions, Webb could reveal which exoplanets might host life. Formation diversity. How do exoplanetary systems form and evolve? Webb's observations could shed light on the diversity of planetary systems and their origins. Super-Earths and mini-Neptunes. What are these intriguing exoplanet types, and what do their atmospheres reveal about their compositions and potential for habitability? Planetary evolution. How do planets change over time? Webb will study exoplanets to understand how their atmospheres evolve and what this means for their long-term stability. Renu Malhotra, an astronomer at NASA's Jet Propulsion Laboratory, exploring exoplanets with James Webb Space Telescope. James Webb once again challenges scientists to rethink our understanding of the universe. In its latest discovery, the telescope has detected a key building block of life at the dawn of the universe, upending what we know about the first galaxies. The discovery of a cloud of carbon in a distant and compact galaxy, just 350 million years after the Big Bang, marks the earliest detection of an element other than hydrogen in the universe. This finding, accepted for publication in the journal Astronomy and Astrophysics, suggests that carbon may have formed much earlier than previously thought, potentially challenging existing models of cosmic evolution. Co-author Roberto Molino, a professor of experimental astrophysics at the Cavendish Laboratory, University of Cambridge, notes that earlier research indicated carbon began forming about 1 billion years after the Big Bang, but this discovery implies a much earlier genesis. This early formation of carbon could influence our understanding of how and when life could have emerged in the universe. The implications of these findings extend to our search for extraterrestrial life. The discovery challenges the assumption that complex chemistry leading to life could only occur much later in cosmic history. It opens up the possibility that conditions for life, possibly unlike anything we currently understand, could have existed earlier than previously imagined. The Fermi paradox and searching for intelligent life. The search for intelligent life beyond Earth has long intrigued scientists and the public alike. The Fermi paradox encapsulates this curiosity: why, despite the vast number of potentially habitable planets, have we not yet made contact with advanced civilizations? The Drake equation, a tool to estimate the number of active civilizations in our galaxy, underscores the uncertainties in our search. Factors such as the rate of star formation, the number of planets per star, and the likelihood of life arising and becoming technologically advanced all play crucial roles in these estimations. However, recent advancements from missions like James Webb are shedding new light on these questions. Webb's ability to study exoplanet atmospheres in detail provides clues about their potential habitability. For instance, recent observations suggest that 55 Cancri e, a super-Earth orbiting a Sun-like star, possesses an atmosphere possibly rich in carbon monoxide or dioxide, challenging previous assumptions about such rocky exoplanets. Challenges in exoplanet studies. James Webb's capabilities also extend to studying diverse exoplanetary environments, from rocky worlds orbiting M-dwarf stars to extreme lava planets. These observations aim to uncover the geological and atmospheric compositions of these distant worlds, offering insights into their formation and evolution. For example, studying exoplanetary atmospheres can reveal whether planets are rocky cores enveloped in hydrogen and helium or mini-ice giants rich in ammonia. Future prospects and discoveries. Looking ahead, James Webb's mission promises more breakthroughs in exoplanetary science. By probing the atmospheres of diverse exoplanets, Webb could unravel the mysteries of planetary formation, migration, and the conditions necessary for habitability across different celestial bodies. Each discovery brings us closer to understanding our place in the universe and whether life beyond Earth is a possibility. Conclusion. In conclusion, James Webb's unprecedented capabilities are transforming our understanding of exoplanets and our search for extraterrestrial life. As we await further revelations from this groundbreaking telescope, we invite you to subscribe to our channel for more updates on the latest discoveries in space exploration. Your support motivates us to continue delivering quality content that explores the wonders of the cosmos. Thank you for watching, and we look forward to sharing more exciting discoveries with you in the future.